Alright, welcome to a video tutorial here on an introduction to trigonometric functions. If you've been watching this video series on trig functions, you're probably thinking, why hasn't he talked about what a trigonometric function is yet? Well, today you're going to get that answer in this video tutorial. We're going to talk about trigonometry as it applies to functions. Alright, so just a little bit of review. Remember that functions are like machines. I've talked about this a little bit in my videos on functions. If you put an x value into this function, you sub in any x, some stuff happens, and a y gets shot out. That's the way functions work, right? It's like an input-output mechanism. And we've seen this when we looked at parabolas and exponential functions. You can pick x values and you can substitute them into your function. Stuff happens. In this case, your x value gets squared, and then a y value gets spit out. Just like the same thing for exponential functions. If you pick x values and you substitute them in, you'll see that you get y values spit out. Okay, well, trig functions work the exact same way. So you can substitute numbers in for x and you get y values out. But for us, in this case, for trig functions, the x values represent an angle on your unit circle. We talked a little bit about the unit circle, but the values that you're putting into your function are the angles that your terminal arm is rotating through. And the y values that come out represent the ratio of these side lengths. So I'm going to do a quick demonstration here. Sorry about that. So here's my unit circle. I'm hoping you can see the whole thing here. So what I've got is the coordinates of my point A here. Remember, the coordinates of any point on the unit circle we can write as cos of the angle between the terminal arm and the x-axis, and comma sine of that angle. So what I've done here is I've just shown you that if I move this point, okay, my angle here, I've just called it angle x, my angle increases. So that's the angle that I'm substituting into my function. So if you picture cos x, picture f at x equals cos x as a function. If I substitute in, let's say, 30 degrees, I'm not going to be able to get it right on 30, but as close as I can possibly get to 30, you get about 0.86 out. So that's what I'm doing. I'm substituting in x for cos, or into cos of x, and I get this value out. Likewise, if I substitute in 30 degrees for x in sine of x, I get 0.5, which, if you remember, if you think back to your special triangles, we know this to be true. The sine of 30 is 1/2. Okay, and that works for any value on the unit circle as we rotate around. If we sub in x values into our function, we're going to get y values out that represent the ratio that we're dealing with. So for the cos function, we'd be talking about the adjacent side to the hypotenuse. For sine, we're talking about the opposite side to the hypotenuse. Okay, just a little demo that I hope illustrates what we're dealing with trig functions here. Okay, so what I've done is I've just kind of generated a table of values here for you using my little unit circle demo. I've got x values from 0 to 360, and I'm going up in 30-degree increments. And I've just shown you the y values that come out as a result. So as I work my way around that unit circle, you can see my y values change, and they change in kind of an interesting pattern. You can see they increase from 0 to 1, and then they decrease from 1 to 0, and then it seems that they're going into the negatives towards 1, and then they start increasing back up to 0 again. So this makes sense because, remember, on that unit circle, once you start rotating your terminal arm around, there's always two values on your unit circle that have the exact same ratio. And you can see that here. For instance, 60 and 120 have the exact same ratio for sine. Likewise, we have 30 and 150. These guys are exactly the same. And it even works for these negative values as well. Okay, so it makes sense that as we work our way around the unit circle, we're periodically going to be revisiting these values that we're getting for our y values. Okay, let me just clean up my chart a little bit here. So interesting properties of these trig functions. You can see the maximum value, the highest value possible is 1. Okay, and the lowest value possible is -1. That's going to be important as we move on into our studies of trig functions here. Okay, the x-intercepts, the values where your y value is 0. You can see I've got one at 0, I've got one at 180, I've got one at 360. Those are your x-intercepts. If you were to keep rotating that angle, or your terminal arm into over 360 through to 720, you'd see that your x-intercepts go up in increments of 180. Okay, so you can test that on your own. The domain here, you can see I could substitute in any angle, and I kind of showed you that with my GSP demo. Any angle is possible. I can substitute any angle for angle x here, and I'm going to get a y value out. Okay, so any angle is possible. That tells me that my domain is the set of any real number of x, or x is an element of the real numbers. For our range, remember the range is the y values that are possible for this function. It's not possible to get any y values outside of the range of -1 and 1, so we specify that in our range. Okay, so what I've done here is I've just made a quick rough graph of what the sine function would look like. Okay, for a moment I just want you to ignore the negative values, but if you picture just starting at 0 for the angle between your terminal arm and the x-axis and increasing that angle, right? We can see if we increase it to 30, when we go over to 30, we're at 0.5 and so on. So we increase on our way up to 1, and then once we get past 90 degrees, we start decreasing. We get to our x-intercept of 180 degrees, and then we continue in that fashion. Okay, and the same thing would happen if we rotated backwards. So if we took this angle, for instance, and we rotated backwards. My GSP demonstration doesn't really show that, but you can take my word for it that that's the case. Likewise, or otherwise, you could just punch in, for instance, the sine of -60 into your calculator, and you'd see that you do get -0.866.